Um, we have different sources of stress during the coating growth, such as generation of residual or internal stresses, which are generated in PVD and CVD coatings during deposition and subsequent cooling from the deposition temperature. So let me write. Residual or internal stresses are usually generated in PVD and CVD coatings during deposition and subsequent cooling from the deposition temperature. Um, During deposition, structural misfits in coating nucleation, that is, structural misfits in coating nucleation and growth, and there is a simultaneous ion bombardment, which can generate stresses of tensile and compressive nature. Simultaneous ion bombardment so this generates state of stress, which can be tensile or compressive in nature. So the most common one is lattice mismatch. So lattice mismatch is most common. So mainly in epitaxial growth, it happens, but also the stresses is given by the coalescence of crystallite during the island growth. Excessively high compressive stresses can result in spontaneous coating detachment. So excessively high compressive stresses can result in spontaneous coating detachment. Example during cooling from the process temperature, or it can happen, that is detachment can happen when the component is externally loaded. So in addition to these factors, Yeah. In addition to these factors, stresses due to mismatch in thermal stresses, that is during contraction process between coating and the substrate materials, and there's a possible phase transformations during cooling, which are superimposed. So we can say that the coating and the substrate have have different thermal expansion coefficient. So thermal expansion mismatch is a common contribution to this effect. So let me write thermal expansion mismatch is a common contribution Now on the other hand, compressive stresses are usually beneficial because in most cases we deposit brittle materials, that is ceramic materials. So we know that the compressive stresses are beneficial to hinder crack propagation. Compressive stresses are beneficial to hinder crack propagation. So because we have to apply inside tensile stresses at least larger than the compressive one, so in order to promote crack growth, so for brittle materials compressive stresses are highly desirable. For brittle materials, compressive stresses are highly desirable. Now moving to the next part. Our main goal is to define deposition parameters which are able to avoid too large compressive stresses and which are able to produce controlled level of residual stresses. So the most common techniques used for residual stress evaluation, techniques for residual stress evaluation. So the most common techniques are first one is the measurement of elastic strains, measurement of elastic strains in the film using X-ray diffraction, or second method is to measure the deflection of thin coated substrates. Um, XRD is the best method to observe crystalline structure or solid materials. So XRD method is the best method to observe crystalline material. Crystalline material or solid materials. So this technique can be applied to crystalline coatings. So we produce a pattern with high diffraction intensity for specific angular positions. So through Bragg's law, we determine interplanar distance corresponding to each angular position. So we're supposed to know the interplanar distances for the unstressed material, typically powder, and then we measure the interplanar distance in our film. And through the diffraction between these two quantities, we estimate the strain existing between our film by this equation. That is change in the quantity upon del D upon the original quantity. So in order to evaluate the stress, we need to have the knowledge of elastic constant. That is, for example, Young's modulus of that material. Line broadening due to the small grain size, dislocations, stacking faults, and microstrains can be an additional source of error during the measurements of the results. Now the alternative method is to um, based on deflection of our substrate. That is deflection of our reference substrate. So this is most versatile method because we can analyze both crystal and amorphous coatings. So as it doesn't matter the structure of our coating, so we can evaluate the deflection of our substrate without any bias. So in the starting point, we have a thin plate substrate. Let me draw. We have a thin plate substrate. So this is our substrate. And which is made of glass or which can be made of, which is made of glass or silicone. So we deposit our film on this substrate, and inside our film we have some types of residual stress which will produce bending effect in our substrate. So if we have compressive stress, then we have a convex profile, something like this. This is our substrate. And we have convex profile, something like this. So this is our coating. So this is our coating, and this is our substrate. And during compressive stress, we have complex profile. This is compressive stress. So compressive stress results in convex profile. Now our system is concave if we have tensile stress, something like this. This is our coating, and this is our substrate, and this is the tensile stress representation, represented by the concave profile. Concave profile. So we can evaluate the nature of stress by just looking at the profile, that is whether it's concave or convex shape, and we can measure the deflection by using profilometry. So deflection can be measured by using profilometry. So according to the substrate thickness ratio, it is in the range of 1:100 to the 1:1000. Because it is required for best accuracy. Deflection techniques can also be used in situ during coating deposition. So if sufficiently thin substrates are used, let's have a look. The formulas used in the experimental investigation of film stress are variants of the equation first given by the Stoney. This equation can be derived with reference to a film substrate combination of width W. Let me plot. Suppose this is our substrate. This is our substrate, and this is our film. Substrate has the Young's modulus, suppose ES, and film has EF, and we have applied stress. Suppose it's DF and DS, and we have applied some sort of stress given in this fashion. So there's some type of profile existing in this fashion which opposes the applied stress. So forces developed in the film are balanced by the opposite forces in the substrate, and the resulting moments will elastically bend the film substrate to pair. So in equilibrium, force F and the bending moment M must satisfy this condition. That is, force is equal to integration of sigma dot dA is equal to 0, and M is equal to, that is, moment is equal to sigma y dA equal to 0. Here sigma is the stress, dA is the element of cross-section area. This is the element of cross-section area, and y is the distance from the chosen axis. It is the distance from the chosen or the reference axis. Now, for sufficiently thin films, that is, for sufficiently thin films, that is when df is very very small than the ds, a simplified expression for stress in the film can be derived. The moment of the force in the film is balanced by the moment of the stress system produced in the substrate, and we can write the equation in this format, that is sigma f w dot df dot ds by 2 is equal to es upon 1 minus es w ds cube divided by 12.1 by r. Here r is the radius of the curvature of the originally flat surface substrate, and mu s is the Poisson's ratio of the substrate. So the film stress, that is sigma f, can be expressed as this equation, that is es ds square by sigma r 1 minus mu s df. So this is called the Stone's formula. So values of sigma f are determined through the measurement of r, and elastic properties of the coating material are not involved in these steps.